Hello, AP Environmental Science students. Welcome back. So my name is Dr. Sowell, and I teach APES down here in Jacksonville, Florida at Darnell Cookman Middle High School. So I just want to do one more time the updates for this year's exam. So you can see when our exam is May 18th, and there are the times below. And then again, only 2 FRQs this year because of our coronavirus situation. Only 2 FRQs, taking it at home, with question 1 being based on an investigation of some sort, either you investigating or you proposing an investigation or parts of an investigation, or perhaps analyzing someone else's investigation. And then the second one is in proposing a solution to an environmental problem. So a little bit more details down here below about what skills you will need to do those. First of all, Ms. Fassler and I just wanted to express how proud of everybody we are. This is a unique situation, and reviewing for an AP exam, at least I know in my classroom, did not look like this for the last couple of years. It's, us all in a room together, hammering stuff out, talking. So this is new and this is different. So the fact that you are back again, slugging through these reviews, bravo, 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 good for you. I definitely want to give a shout out to Neil from Chico, California. Neil, if you're out there, keep up the good work. He and I have been emailing back and forth. He's doing this as an independent study. So bravo for those of you who are doing this on your own, which is even more of a challenge, but everybody keep up the good work. So let's start with the homework from Ms. Fassler. This question starts us off with the U.S. Forest Service ecologist periodically sampled plant diversity on Mauna Kea, Hawaii between 2000 and 2012 during a 12-year period of drought, keyword there, to determine the relative abundances of native hardstem lovegrass versus non-native fountain grass. I'll reiterate what Ms. Fassler said here yesterday. Slow down and read the entire question before you start to answer. Now, you may have your own strategies, but that's the strategy I tell my students. Slow down and read every word so that you know what the entirety of the question is asking, as opposed to what I might be asking, for example. And so there's the opening here, and then it gives you a graph. So we can kind of look at the graph in terms of the axes. What are the 3 data sets that are displayed on the graph? The title, the abundance of 2 different grasses between 2000 and 2012. I know when I first read this FRQ, I kept stumbling on native hardstem lovegrass, non-native fountain grass. I mean, they're both grasses, they both have complex names. So that was a place that I know I had to slow down a little bit. So let's start looking at some answers. So A said, describe 2 characteristics of invasive plants that help them outcompete native plants. So your description, not an identification, needed to include how that helps them outcompete native plants. So this is worth 2 points, 1 for each. You could have said something about the range of tolerance. Perhaps they have, there is some abiotic factor of their environment that the invasive species are more tolerant of in terms of extremes than the native species. That would give them an advantage. They might be a generalist. So that gives them a little advantage over native species that maybe are more specialist. And then the category of being our selected species or our species, our strategists, is a huge characteristic because they typically propagate or reproduce earlier in their life cycle. And when they do, they reproduce a lot. Think of like a fern, for example, millions and millions and millions of spores coming out. And so you could also talk about invasive species lacking natural predators or diseases that would control their populations. So any of those 2 descriptions would have gotten you points here for A. B really has you looking at the graph. So it says, based on the data in the graph, tells you right there, look at the graph. Identify the year in which the abundance of native plants versus invasive plants is nearly equal. So you could go over here, and here's our invasive and native, and where are they most equal? Right around there. So you pick a year, and it could have been 2001 or 2002. So a little piece of FRQ advice. If you are asked to identify a value from a graph, pick a value. What would not get you points typically, and I can't say this is a rule everywhere, but typically you would not want to say the year in which the abundance of native plants is nearly equal to the invasive is somewhere around 2002. or somewhere between 2000 and 2004. That's not identifying a value. So it says identify the year, not a range of years. Little advice. Then the next one says describe the change. So in overall abundance. So overall abundance is this one right here. So it's going from around 340 down to about 300. Again, this word is important. It says describe, not identify. Identify might be, it goes down. But describe, well, you need a little bit more of a description there. So you could say something like the plant abundance decreases from approximately 300 plants per square 100 meters down to 300, or you might say it decreases approximately 10%. So again, you're providing some description of the change, not just saying, it went down. I explain what the trend in relative abundance of native hardstem lovegrass and invasive fountain grass over the 12-year period implies about each species' ability to withstand drought conditions. First thing you should key in on is the word explain, and remember those task verbs mean something. So explain how or explain why something. I've given you a reminder here. So it says provide information about how or why a relationship, process, pattern, position, situation, or outcome occurs using evidence and or reasoning to support or qualify a claim. So there's a description part of this, but then there's also a justification. There should be some verbs in there that you know what you're talking about. So here is an example. Over the 12-year period of drought, the relative abundance of native hardstem lovegrass decreased, while the abundance of invasive fountain grass increased, period. This would imply that the invasive fountain grass is more drought tolerant than the native hardstem lovegrass. That's an explanation. C, explain, there's the word again, how a loss of species diversity would affect the stability of an ecosystem. And I know I've mentioned this before in Unit 1, and Ms. Fassler mentioned it the other day, that there is a relationship between species richness and biodiversity and the stability of an ecosystem. How resistant is the ecosystem to change, and then how resilient, how much can it bounce back from that change? And so again, think about the relationship between the stability of a tundra versus the stability of a tropical rainforest, for example. But in this case, we're looking for how explaining a loss of diversity would affect the stability. So you could say something like, the greater the species diversity, the better it can withstand stressors. And so you could also say ecosystems that have a larger number of species have a greater chance to recover more quickly from a disruption. So the conversation we had the other day about disruptions and disturbances, how ecosystems respond to that is related to species biodiversity. And then finally, if you look just at the plant species themselves, the greater the biodiversity there, the greater the productivity for that whole ecosystem. Remember, we talked the other day about NPP, net primary productivity, being the battery that drives the rest of the trophic levels above it and supports the whole food web. So that would give you a more stable trophic structure as well. And D, last part, based on the data in the graph, the Forest Service decided that a coordinated attempt should be made to remove the non-native fountain grass to protect the native grasses, following an integrated pest management approach, IPM. Okay, so they're going to do an IPM approach to reduce this invasive species. So first, DI says, describe IPM. Well, remember, describe is provide the relevant characteristics of a topic. So what are the relevant characteristics of a topic? When I think of IPM, I think of in contrast to just a blanket use of broad spectrum pesticide. I kind of think about its opposite. So instead of a blanket use of broad spectrum pesticide being your only strategy to reduce pest, IPM, I think of a more holistic approach that involves using biological control, chemical control, physical controls, reducing that pest population down to a manageable level that is economically tolerable. So that's what I think of. So let's see what the answer here says. Integrated pest management is a combination of methods used to effectively control pest species while minimizing the disruption to the environment. I think that's a nice point there, especially limiting the introduction of chemicals into the environment. These methods include physical, biological, and limited chemical. Remember, a characteristic of IPM is not that we do not use pesticides, it just means that we use them in a measured way, in a limited manner. And finally, we've gotten to the experiment part. So it says the ecologists want to begin their IPM program with a physical control in a managed area and establish a 10-hectare plot in which they will test their efforts. Based on the data in the graph and the information provided, identify a testable question. So they could ask, how will the physical control or removal of invasive fountain grass affect the relative abundance of native hardstem lovegrass? Maybe down here, how will the local environment respond to the physical control or removal of fountain grass? So when you're trying to identify a testable question, remember it's ideally both the independent and dependent variables are reflected in the question. And then the way those variables are described, you can clearly see how they could be quantified or what kind of data collection you might make for both of those. And then the last part, describe a research method that they could use. So again, this is part of that scientific experiment skill that we looked at before. So you could say as part of that experiment, they could physically remove the fountain grass on an identified schedule and then do nothing to the love grass. Or if we jump down to the bottom, you might physically remove both types of grasses from the test plot at the beginning of the trial and then reseed the area with hardstem love grass. So the question is asking you for a description of a reasonable keyword there, research method that they could use in their control efforts. So many possibilities for that. All right, so hopefully you did well on that FRQ. I'll leave you with an FRQ for homework tonight as well that Ms. Fassler will go over tomorrow. So what are we talking about today? We're talking about us people. So Ms. Fassler did a brilliant job yesterday of talking about the population dynamics of animals and plants, talking about R species and K species, talking about carrying capacity, things that limit the biotic potential of a population. Well, we obviously are animals as well. We're a species on this planet, but we don't typically follow sometimes the pattern that a warren of rabbits might follow in a field. So we're going to look at some differences today, some things that make human populations unique and different. So our goal, we're going to look at age structure diagrams. We're going to look at total fertility rate, basic human population dynamics, and then the demographic transition. And then through doing that, we'll also look at visual representations and data analysis. I think that for this particular lesson, it's useful to kind of go back and get a bigger picture. So remember, our overall enduring understanding is human populations change in reaction to a variety of factors, including social and cultural. Now, when Ms. Fassler was talking about populations of a fish species or a rabbit species or a lynx species, those didn't include social and cultural factors. Here we do a little bit more. I think this is a perfect place to really emphasize visual representations and models, from the ability to just describe the pieces and parts going on in that model, and then going all the way down to say, okay, I understand this model. How can I use it in a new context? I mean, clearly we have two essential visual representations or models here in this unit. Is we look at the age structure diagram and the demographic transition model. All right, so what do we really need to know? So let's start with Unit 3, Topic 6, and this is our age structure diagrams. So after we chat for a few minutes, you should be able to explain age structure diagrams. That's a good goal. So how are we going to get there? We're first going to describe just what's going on inside of an age structure diagram, not really use it, just who are the pieces and parts, who are the players, what's being told there. And then we're going to use that model to explain population growth. I do want to point out that sometimes you will see age structure diagrams described as population pyramids. Those words are not 100% interchangeable, but a lot of times you will see one versus the other. We, in our curriculum, typically follow age structure diagrams. That's the wording we use. All right, so here's one. This is the age structure diagram of Uganda from 2020. I just pulled these a couple of days ago. Here's another one. This is us, the United States this year. And here's Japan. The first thing you should recognize is they all look different. So if they look different, that means they're telling different stories. And I should be able to look at an age structure diagram and come to a more robust understanding of what's going on in the population dynamics of that particular country. Age structure diagrams typically are done on a country level. So let's just break down the pieces and the parts here. So this is the United States one for this year. So the first thing you'll notice is we've got a male and a female side. The left side here is male, the right side here is female. On the bottom, you can see population, and on the y-axis, you can see age. So just as an example, in 2020, there were approximately 10 million females between the ages of 0 and 4. That's how you could read a piece of that data. That age group is particularly useful from 0 to 14 because we call that the pre-reproductive cohort or group. So the pre-reproductive group is 0 to 14. Then we have this bigger chunk that is reproductive, 15 to 44, and then post-reproductive after 45. Now, obviously, a female can have children before or after these strict demarcations here, but this is an average. This is just a cohort definition to use. So those come into play in a little bit. All right, so let's look at these three age structure diagrams and look at that particular grouping. So if we look at Uganda, the vast majority of this age structure diagram is composed of this young pre-reproductive group. As opposed to the United States, it's almost in line with some of the other cohorts above it. Whereas Japan, this pre-reproductive group is much smaller than what we have above. So these three countries give us an example of what we can do by looking at that pre-reproductive stage. What we're looking at here is population momentum. So this is a prediction of future growth. The higher the percentage of people in that pre-reproductive cohort, the more the population will grow as these individuals mature into the reproductive cohort. Meaning, if the country of Uganda has a very, very large pre-reproductive group, that means in the near future, they will become part of the reproductive cohort and population will continue to grow. The United States, growth will probably be a little less, pretty stable. And then in Japan, we can see the number of individuals at the pre-reproductive level are quite smaller. So that may indicate a slower or even a negative population momentum in the near future. This inverted pyramid shape of Japan is particularly useful to understand the fact that this might put social pressures on the economy and the social system of Japan because the vast majority of the population are older. And typically, in most societies, the older generations, because they're no longer working, rely on the economic and social support of the younger generation. Well, in this case, we've got a much stronger population of older individuals than younger individuals. So just the shape of the pyramid alone can tell us something about what might be going on in the society. The rule of thumb is this: a rapidly growing population will, as a rule, have a higher proportion of younger people compared to stable or declining populations. In other words, when you look at an age structure diagram, if it has a very large base, future growth will be higher than if it had something like Japan's, which is a negative growth, okay? So we've been talking about growth rate. We represent that by R. We saw that with Miss Fassler yesterday when she was talking about the population growth graphs that she was looking at. Now, this is typically expressed as a percent, an R as a percentage. Now, we know on the AP exam this particular year, you will not be asked to perform calculations. So I am going to show you how to calculate R, but not because I assume that you're going to have to, because you won't, but you may be presented with data like R values and have to make an interpretation based on that. So while you may not have to calculate R, you need to understand how R is derived and what it means. So basically, the growth rate is birth minus death over 10. That's the basic formula. Now, there are also issues of immigration and emigration, but we're not going to deal with those at this point. So let's just take Japan, for example. Japan this year has a crude birth rate of 7 births per 1,000 individuals. We can just really relate that as a birth equals 7. The reason we can just reduce that to 7 is we're making a percentage here. So because this is already over 1,000, we reduced it to 7 and then divide by 10. That's probably a bad explanation, but all you really need to know is the growth rate is birth minus death over 10. So in this situation for Japan, 7 minus 10 divided by 10, So we're looking at a negative 0.3% growth rate. So that means that this population is not growing, it's shrinking by a rate of negative 0.3%. That's R. So here's the R's for those three countries we were looking at. So Uganda is 3.3, very high growth rate. Japan is negative 0.3, it's slowing down, going negative. And you'll see the United States is 0.7. So it's pretty stable. It's not as big as something like Uganda would be. So again, shape of the pyramid, you should be able to kind of relate that to its R, or its growth rate. You can also look at one country over time. So here we were looking at 3 different countries for this year. You could also look at one country over time. So this is Brazil in 1950. Now, just on this snapshot of a moment, you should be able to start telling a story, maybe perhaps of the percentage of pre-reproductive individuals, what might that indicate for their population momentum and future growth rate. And then if we start looking at over time, that's 1950, 1960, 1970, 1980, 1990, 2000, 2010, and this year. So it's really interesting. If you just looked at 1960 to 1970, really didn't notice some difference. There's some reduction in some of the numbers. But when you really compare these 2 years at the end, or the beginning and the end, 1950 and 2020, huge difference. Their population structure looks different. Their age structure diagram looks different. There's something different going on in the society of Brazil in 2020 that wasn't going on in 1950. And so we could look at things like industrialization or development, urbanization, education, income levels, but also cultural influences. So I'm going to let you listen to an NPR story. It's a couple minutes long that really dives into some of the, quite unique and fascinating things that would take a country from an age structure diagram that looks like this to something like this today.
In Brazil, there's been a demographic shift that has astonished social scientists. In 50 years, the fertility rate tumbled to fewer than 2 children per woman on average, lower than in the United States. Demographers say it's because the country is richer and more urban, but they also point to Brazil's hugely popular soap operas and their portrayal of small, glamorous families. NPR's Juan Ferrero has the story from Rio de Janeiro.
Veronica Marquez has a husband, a nice apartment in a trendy district, and a career she loves. Talking in a restaurant near her office in Rio, Marquez explains that she's 31 and doesn't have children.
I'm planning to have kids when I have a bigger career, when I raise more money, and maybe when I have my life in another step.
And when she does have kids, she says, it'll be 2 tops. Smart, educated, ambitious, Marquez is typical of a growing number of Brazilian women who are focused more on their careers. If she does have 2 children, it'll be right in line with the average these days for a Brazilian woman. Barely 2 generations ago, it was 6 children per woman. Then the fertility rate in Latin America began to plunge, though it was most pronounced here in Brazil. The latest figures, in fact, show that the fertility rate stands at just under 1.9 children per woman, says Susana Cavenaghi, a demographer in Brazil's Census Bureau.
There are a lot of reasons for that drop in Brazil, and most of them has to do with the modernization, this new way of thinking. Women are modern, and they take care of their own life.
Brazil's fast urbanization means millions of rural poor migrated to cities where big families are a financial drain. And in a country where abortion is illegal and the Catholic Church frowns on birth control, women have embraced family planning any way they could, says Cavenaghi.
They have more to say about their reproductive life than the men. Men interfere less in their lives than would in other countries.
And there's another factor, one documented in studies by the Inter-American Development Bank and the University of Texas, the role of the telenovela, or soap opera. In Fina Estampa, the most popular of Brazil's telenovelas these days, the characters are often rich and cosmopolitan and have few children, if any at all.
Ai, meu Deus, Solange, você tá indo rápido demais, amiga. Homem não gosta de mulher que toma iniciativa desse
It's
jeito,
been a
não.
recurring theme in soaps for decades,
Meu
says
Deus,
Maria
deve estar
Lopez of the
assustada.
Center for the Study of the Telenovela.
Eu creio que não há dúvida de que a telenovela
She says
hace
there's
parte
no
desta
doubt that the appealing
disminuição
lives presented in the
da
soaps play a
população do
role in
Brasil.
the falling fertility rate. Other factors also are at play, including the expanding role in the workforce for Brazilian women, whose educational level has also soared. Still, it's not just the educated and affluent who've seen the fertility rate plunge. Demographers say they see it among the poor too, and in rural as well as urban areas. At a new restaurant in a working-class district on Rio's outskirts, the 5 women owners all come from big families. Priscila da Silva chops tomatoes in preparation for the lunchtime crowd. She says times have changed.
Antigamente eu queria ter 4.
Before, I wanted 4 children, she says, and had even picked out names. But now I just want one, she says.
Devido à situação de hoje em dia, você criar filho está muito difícil.
It's too hard these days, Silva adds. You have to pay for schooling, for health care. There are all kinds of costs. And besides, she says, she's got a growing business to run. Juan Ferrero, NPR News.
So I just think that's really cool. It's great to hear the actual voices of the individuals experiencing these changes as opposed to just hearing me blah, blah, blah about it. So one of the things they mentioned in there was total fertility rate. So this is Unit 3, Topic 7. And so basically the total fertility rate is the number of children the average woman has in her lifetime. This is on average per country. So what might affect that? Well, you heard a lot of those things in the story, but the age at which females first have a child, what is culturally and socially the norm for that particular country. Educational opportunities, huge impact on total fertility rate. To what degree females are educated in that country. Access to family planning, government acts and policies. You may have heard about the one-child policy in China, for example. Other countries have other policies or acts or laws that might have been placed in terms of population control. So if we look at TFR, total fertility rate, over the course of the last 60 or 70 years or so, so in 1960, the global total fertility rate average was around 5. That means the average female on the planet, female human being, had 5 children on average. Now, a little less than half of that, 2.4. So we've seen a dramatic decrease in the number of children. Why? There are many factors. So here are the two from the ones that we looked at before. Right now, the total fertility rate in the United States is around 1.8, meaning the average woman in the United States is having 1.8 children, as opposed to Uganda, which is 3.3. Now, that's useful in terms of comparing it to this concept called replacement level fertility. If we have 2 people and they have 2 children, they've replaced themselves. So that means that when the 2 parents die, they're replaced by their 2 children. So replacement level means you're simply replacing the parents. And ideally it would be 2 because, 2 would match. But because there's so much infant mortality in certain countries, it's actually a little higher than 2. So if we compare this replacement level fertility with total fertility rate of a country, we might be able to see a relationship there. And so if the fertility rate is at replacement levels, a population is relatively stable. So that's kind of where the United States are. We're a little bit lower than replacement level, but we're not seeing the massive population growth that Uganda is because their total fertility rate is much higher than the replacement level fertility. So I mentioned before that one of the reasons that replacement level fertility is higher than 2 is because of infant mortality rates, the number of children below the age of 1 that die per 1,000 births. And in some countries, it's much higher than others. And for the reasons you can probably guess, so access to clean water and nutrition or sanitation, prenatal care is huge. And again, education of females. So if we look at infant mortality rate globally, in 1990, we were looking at a very high value, close to 65, but now we're looking at something around 29. So the global infant mortality rate has decreased as well. But it's really interesting to think about what's going on within a country. So far, we've been talking about Uganda as if it's all the same, or the United States as if it's all the same. Well, we know we're not. And so the infant mortality rate actually is different in different parts of our country as well for socioeconomic reasons and other reasons as well. So here are the 3 countries that we've been looking at. So the infant mortality rate is 33 in Uganda. That means out of every 1,000 live births, 33 do not make it past their first birthday. Whereas the United States, it's an average of 5, and Japan, it is 2. So we're starting to kind of throw these numbers onto these 3 countries in terms of replacement level, fertility, growth rates, total fertility rates, infant mortality rates. You should have a kind of a range of what's acceptable or normal. So you wouldn't have an infant mortality rate of 3,000, for example. So you've got to kind of think of what's normal for these values and then start putting them together to tell a story of what's going on in a country. So now we're going to move into kind of the world as a whole. So by the end of this particular section, 3.8, you should be able to explain how human populations experience growth and decline. So to get there, we'll look at the idea of the carrying capacity for humans on the planet. We'll describe factors that affect our overall population change. And then we're going to talk about this little discrete rule called the rule of 70. So here is a screenshot of the US Census, the World Census. I just grabbed it a couple hours ago. So you can see currently the US population is 329.5 million people, whereas the world population is at 7.6 billion people. And here you can see the top 10 most populous countries. I think it's interesting to look at China and India, how close they are. Most demographers agree that India will take over the first place from China soon. United States, Indonesia, Pakistan, Nigeria, Brazil, Bangladesh, Russia, and Mexico rounding out the top 10. It is interesting to note here, on an average, there's 1 birth every 8 seconds on the planet and 1 death every 11 seconds. Right there tells you that we're, this is clearly an average. This is not something that is country specific. This is an average everywhere. So just have a general idea of what the population of the planet and of the United States is. So let's look at the world population. The overall growth curve here is exponential. It's growing at a higher and higher rate, especially since the Industrial Revolution. And if you remember the conversation yesterday from Ms. Fassler, we don't see us experiencing the effects of a carrying capacity here. We're not seemingly being limited by the environment, the environmental resistance or stressors in the environment. Contrast that to the conversation that you had yesterday about carrying capacity in other organisms, where that biotic potential is counteracted by the environmental resistance to create the carrying capacity, the relatively stable population size. This population is limited by the environment, factors in the environment. So the question that should immediately come to your head is, well, where's our carrying capacity? So at some point, are we going to experience the same thing that the other organisms do? Some people argue that we've already passed our carrying capacity. Some people argue we haven't reached it yet. And it's useful to start back with someone named Thomas Malthus. So this is late 1700s. He described population this way. He said, okay, the human population is growing exponentially. So here's his curve right here, the exponential population growth of humans. But he said, unfortunately, food production is pretty linear. We don't see that exponential growth in food production. So at some point, we're going to reach this catastrophe point, the point in which we just don't have enough food. And so population is going to start to decline. Some people disagree with that and say that because of the creativity and agricultural innovation that we've accomplished, we simply increase the carrying capacity. So just think about all the things that are involved in the Green Revolution or all the current modern agricultural practices that greatly increase yield. Well, maybe that's enough to raise the carrying capacity for human beings on the planet. So overall, what influences that other than food production? Well, birth and death rates clearly, infant mortality rates, access to family planning, good nutrition, education of females, and postponement of marriage. You should start seeing some patterns here at the country level and at the global level. Now, we could stop and go into lots of case studies here. We could look at, education of females in Nigeria, for example, or we could look at the one-child policy in China, or some of the educational programs in Brazil. But they all have these common themes going on. So instead of going into those case studies, I thought we would just take a broader look here and look at the themes. So it's also affected by density-independent factors, like a hurricane or a fire or a drought, as opposed to density-dependent factors such as food and water, other resources, disease, or territory size. So Ms. Fassler started this conversation the other day, reminding you that a hurricane is going to have the same destructive power to a population, whether the population is small or large. The density of the population does not impact the power of a hurricane, as opposed to something like disease, in which we know the proximity and density of organisms can speed up the transmission of that disease. So density independent, density dependent. And then finally, we get to this rule of 70. And again, you will not be asked to do calculations on the exam, but you may be asked to interpret what a doubling time means. So basically, the rule of 70 says, what's the average, or what's the estimated number of years it'll take for a country's population to double? So the formula is pretty simple. The doubling time is 70 divided by R, expressed as a percentage. So for example, right now, with our growth rate at 0.7, it will take 100 years for the United States to double its population, as opposed to Uganda right now, if everything stays the same, they will double in 21.2 years. So you should be able to think about the relationship between doubling time and economic development of a country and its place on the demographic transition that we'll look at in a few minutes, or right now. So this demographic transition, this is a great model, and it's a great place for us to practice our visual understanding of a model and looking at a graph. So to get to this understanding of the demographic transition model, we'll first just describe it, what's going on inside that model. And then we'll look at some comparisons between those age structure diagrams we did at the beginning and this demographic transition here. And then finally, we'll end today with looking at some basic characteristics of developing and developed countries and where they may fit along this model. So let's just pick apart the model at this point. So first thing you'll notice at the bottom is time. So this is years at the bottom. Time is at the bottom, the x-axis. And then on the y-axis, or at the very top, we've got these labels: stage 1, stage 2, stage 3, stage 4. Let me stop here and say that AP Environmental Science uses the 4-stage model of the demographic transition. Some places you will see a 5-stage model. What's going on inside the model doesn't change. It's just a change in where they've made these delineations into separate stages, okay? But we use pre-industrial, transitional, industrial, post-industrial. On the left-hand side, we have birth and death rates. We've talked about that before. And on the right, we have the population size. So let's kind of go through from left and right and see what story this model is telling. So at the beginning, when a country first begins its travel through the demographic transition, its birth and death rates are going to be relatively high and relatively equal. So if there's an equal number about of birth and deaths going on, the population is going to be pretty stable. It's very rare to find societies like this on the planet still today. This is characterized by, lots of warfare and instability, struggling for resources, clearly no healthcare, medicine, education, things like that. But as a country moves out of that, we get into this transitional stage where something really unique happens. And this is definitely a place for you to think about birth and death rates. So the first thing that starts to happen is we see this drop in death rate. So infant mortality rate starts to go down. We start seeing improvements in healthcare and medicine. So the death rate goes down. However, the birth rate kind of stays where it was for a while. And if we have many more births than we do deaths, the population is going to increase. So this kind of gap between these lines here pushes the overall population forward. And then we start to see the birth rates coming down to meet the death rate. So death rate drops first, birth rates drop, and if birth and death are getting closer together, like they were over here, we should start seeing a decrease in the population, or a stabilization of the population, and then eventually a decrease. The population should decrease if the number of deaths are now more than the number of births. So we can imagine a country over a long period of time going through every single one of these stages. And currently today, we have some countries here in the very end of this post-industrial stage, and we still have some countries at the transitional industrial stage as well. So here's an example of one of those that was 5 delineations, but the story of what's going on is still the same. I want to point out the reasons for changes in birth and the reasons and changes for death. So one of the key reasons why birth rates are still high up here is because this is typically going to be a more agricultural society, and many children needed for farming. We still have a rather significant infant mortality rate, but social and cultural reasons, as well as a lack of family planning, all feed into the birth rate still staying pretty high, whereas the death rate has dropped. There's less disease and famine, there's better health care, better water supply, and then eventually we get to a place where those things even out at the same level, and we start to see a population decrease. And we see that with family planning, good health care, improving status of women, including education, and later marriages. And we started to hear that in the conversation of some of those Brazilian women in the NPR story. So now let's see if we can tack on some of those population pyramids to this model. They don't coincide 100% perfectly, but you should be able to look at a population pyramid and kind of figure out where it might land on the demographic transition. So for example, as we move from pre-industrial to transitional and into industrial, we still have this large base, this high population growth, lots of individuals in the pre-reproductive cohort. But then as we start to go through the industrial stage, we start to even out. So we get a little bit more stable population. And then finally, something like this, where we would start to see a decrease in the base of the pyramid. So for any one of these, like this one, for example, noting its place on the demographic transition and its shape, could you tell stories about this country? Could you maybe speculate on infant mortality rate or economic development or status and education of females? Those are the things that you would be asked to do on an exam. All right, so then we're going to end today with this idea of developing versus developed countries. It's not, clearly countries are very heterogeneous, and we can't categorize a whole country as developed or developing. Some textbooks will use LDC and HDC, less developed and highly developed. But if we paint with a broad brush, we want some generalizations, we can typically say levels of industrialization and income play a role here. So less industrialized and less overall income, going to be developing countries. Total fertility rates and infant mortality rates would be higher in a developing country. Number of children in the workforce, especially in the agricultural fields, is going to be higher in developing countries. Population growths are going to be stronger in developing countries because their birth rate is still high. And then as you become developed, you're going to have better nutrition, sanitation, clean water, education, healthcare, all of those things. So I want to end with playing just a minute or two of the population pyramid TED Talk that I use.
Russia, with the largest territory in the world, has roughly the same total population as Nigeria, a country 1/16 its size. But this similarity won't last long. One of the populations is rapidly growing, while the other is slowly declining. What can this tell us about the two countries? Population statistics are some of the most important data social scientists and policy experts have to work with. But understanding a country's situation and making accurate predictions requires knowing not just the total size of the population, but its internal characteristics, such as age and gender distribution. So how can we keep track of all that data in a way that makes it easy to comprehend? Complex data is more easily interpreted through visualization, and one of the ways that demographers represent the internal distribution of a population is the population pyramid. Here, the data is divided by gender, with females on one side and males on the other. The population numbers are shown for each 5-year age interval, starting from 0 to 4, and continuing up to 100 and up. These intervals are grouped together into pre-reproductive, 0 to 14, reproductive, 15 to 44, and post-reproductive years, 45 and up. Such a population pyramid can be a powerful predictor of future population trends. For example, Rwanda's population pyramid shows it to be a fast-growing country. With most of the population being in the youngest age groups at the bottom of the pyramid, the number will grow rapidly in the coming years. As today's children reach their reproductive years and have children of their own, the total population is almost certain to double within the next few decades. For our second example, let's look at Canada, where most of the population is clustered around the middle of the graph. Because there are less people in the pre-reproductive age groups than there are in the reproductive ones, the population will grow more slowly as the number of people reaching their reproductive years decreases. Finally, let's look at Japan. Because the majority of its population is in its post-reproductive years, and the number of people is smaller at each younger interval, this means that at current rates of reproduction, the population will begin to decline as fewer and fewer people reach reproductive age.
So I will highly recommend you taking a look at the second half of this. It's really interesting. They go into a little bit more detail about different countries. And it's easy to find if you just Google demographic transition or population pyramids TED Talk, you'll find it. It's really interesting. So let's do some rather quick, looking at time here, examples. So during which stage of the demographic transition shown above does a population begin to experience an explosive increase in growth? So where does it begin? So you've got stage 1, stage 2, stage 3, and stage 4. Well, the answer here would be stage 2. This is when you would start to see that big uptick in population size. Here's an example of a test question where you're asked to look at an age structure diagram. A country with an age distribution like that shown in the figure above is most likely a country that is experiencing rapid growth, slow or no growth, high death rate, 40% of the population under 15, or is a less developed country. Well, because it's really almost straight up and down, that points to slow or no population growth. All right, I'm going to skip that question. Feel free to go back and look at it. And then I want to point out our homework for tonight. So for today, we went over age structure diagrams, TFR, human population dynamics, and the demographic transition, all kind of helping you to understand that human populations change in reaction to a variety of factors, including social and cultural. So for homework tonight, again, remember your task verbs, look at them, look at them, look at them. They mean something. I'm going to have you do this FRQ. And the first thing you should see is it starts with some age structure diagrams, and then there's an A, B, C, and D. Just as a reminder, anytime you see a diagram, stop and try to digest it. There's a strategy I like to use with my students called I-squared, in which you first identify and then interpret. You first go, well, what do I see? And you just simply identify things in the graph that you see. You don't try to interpret them yet. And then you go back and add a what does it mean statement to each one of those things that you saw. And that helps you to build a robust understanding of the story that the graph or the image or the model is trying to tell you. It would be like trying to understand all the characters in a movie and the plot at the same time all at once. Well, no, you build up the characters and eventually you tell the story. Just like this, you need to build up what all the pieces and parts of this are to tell the story. If you're interested, that strategy is called I-squared. And if you use the link below or you just Google BSCS I-squared strategy, you should be able to find it. It's not a strategy I would recommend for use on the AP exam because it does kind of take a long time. But if you practice it several times with several different graphs and visual images, it will help your ability to do that. So again, take a look at this homework, and Ms. Fassler will go over the questions A, B, C, and D tomorrow. Just a reminder one more time, we know that not all students have access to the internet or a device. We're working on solutions to help students get what they need to show their best work. If you need mobile tools or connectivity or know someone who does, you can reach us directly to let us know. All right, apes, it's nice to see you again. Bye, see you next time.